Hi. Now that we've introduced what density altitude is, we are going to try and apply it to the real world in terms of flying an airplane or a helicopter and cover some of the things that are kind of sneaky that cause not only misunderstandings about density altitude, but it can also cause pilots to make some potentially fatal mistakes. So we're going to start with what is normally taught, and all of this is correct. It just does not go far enough, in my opinion. So we're back at the takeoff performance chart for the Cessna 152, and we're going to apply it to a specific scenario. We're going to apply it to start with, sea level on a standard day. So our pressure altitude is 0. We're out there at an airport on the coast on a perfectly standard day. And so the outside temperature is 15 degrees C, which is standard at sea level, which is inconveniently right between these two columns. But if we do the math, the numbers that fall between those two columns for this row that represents sea level is a 725-foot takeoff roll and about 1,340 feet to clear a 50-foot obstacle. Now, if instead of taking off at sea level on a standard day, we take off at 3,000 feet on a standard day. So this would be maybe someplace like Madras. And we're going to take off. Standard temperature at that altitude is 9 degrees C, which is close enough to the 10-degree set of columns for our purposes, which means we have about a 925-foot takeoff roll and 1,730 feet to clear that 50-foot obstacle. So you can see it increased both our ground roll and our 50-foot obstacle clearance distance considerably. Now here we are up at a higher elevation airport, 6,000 feet. And although everything is still standard pressure, standard temperature, we can see that we've lost a lot of performance already. So far we've been dealing with just standard pressure and standard temperature. And when both the pressure and the temperature are standard, then our actual above sea level altitude is the same as the density altitude. And when that happens, it doesn't mean that you've got great performance. It just means that you get the performance that you might expect at 6,000 feet above sea level, which is not very good. Here it's going to take us 1,145 feet just to get off the ground, and then 2,200 feet just to clear a little 50-foot obstacle. So now we're going to talk about some of the sneaky things. There are a lot of these, and so it would have stretched out into a long video. We're just going to cover the first one in this video, and then you're going to have to look at the other videos to look at the rest. In each of these sneaky things, I have coded them with these little icons to indicate whether they affect airplane or helicopter or both. And this first one affects both. Sneaking thing number one is that we instructors very rarely draw these little diagrams to scale, and I'm as guilty of this as any instructor, and that's because drawing them to scale is difficult. This is what the same drawing would actually look like if it were to scale, because a 50-foot obstacle is a very small part of a 2,000-foot runway. And so you end up with a very shallow climb gradient at 6,000 feet, even if it's standard temperature and standard pressure. That's an important thing for you to internalize. We get in sort of a habit of assuming that we're always going to be, clearing 500 or 1,000 feet by the time we end up at the end of a long runway. And that's just not true at higher elevations. So you need to internalize that very shallow climb gradient. This is not nearly the end. Please continue on with applied density altitude, sneaky things number 2 through 4 next.